and welcome back. In the last lecture, we talked about DFAs. In this lecture, we're going to move on from DFAs to something very, very similar to a DFA, but that is a little less strict. Let's just start by having a little bit of a review of what we know about DFAs. So for example, if I have this DFA, and we consider these different strings that I've got here. As the DFA runs, if we say it's running, now you can see kind of why I said it's sort of like a computer. As this DFA is running, every step consumes a letter in our string. So for example, if we're looking at this string, we start with that first A, and we take that step. Next A, we end up at state 2. Now we've got a B, we stay at state 2. Another B, we stay at state 2. Another B, we're still at state 2. We finished, and we finished at a double circled state, which tells us that this string is in the language. Okay. If we look at the second string, we see an A, so we transition from 0 to 1. Of course, we're always starting at 0 because that's where start is. We see a B, we go down to state 3, another B, stay at state 3, another B, stay at state 3, another B, stay at state 3. We've completed stepping through the string. We are at state 3, which does not have a double circle. And so that tells us that this string is not in our language. And similarly, let's do that last string. There's our B. We follow that down. The next B, we're in this trash state, right? So we're not getting out of here. Another B, the A. So we end up at state 3. And state 3 is not an accept state, so that last string is not in our language. And what were the other things that we know about our DFAs? Well, we know a DFA always has to have a start state, and every state has to have an out transition for every letter of the alphabet. So if I tell you this is a DFA, then you can tell me, well, if that's a DFA, then the alphabet for this thing must be simply the set AB. Okay? We also know that you have just one start state, but you can have 0 accept states if you want, 0 final states, or you could have as many as you have states. Okay, so here's a whole bunch of DFAs that I'm suggesting we should do. I'm not sure we'll do all of these, but let's see. So let's shrink this. So a DFA that recognizes the language, the empty set, right? Well, the simplest one I could draw may look like this. I've got my start and a single state. This says over the alphabet AB, so I'm over AB. I'm sorry, handwriting on this iPad is difficult, but there is my start state, AB, no double circle, so accepts the empty set. I mean, we could also say, you know, AB. There's another DFA that accepts the empty set, right? Here's another DFA if I add a state 3, and I could add a state 4, right? I mean, there's an infinite number of, an infinite number of DFAs that accept the empty state. That's B. But just the singleton by itself is the simplest. Okay, let's try and do that next one, the set containing just lambda, right? So it's a DFA that only accepts the empty string. You may want to pause before I do all of these and just try them on your own, right? But let's do these. I'm going to go through them relatively quickly. So we accept the empty string, so that state's going to be an accept state. But if we see any symbols, an A or a B, we'll go to state 2, which will not be an accept state. And we will have a loop like that. So empty string gets accepted, everything else goes to state 2, which is a garbage state, a trash state, right? Keeping in mind that Dr. K's trash state is just something I use. It's not a general term that's used in the DFA community. Next one recognizes the language, the set containing just the symbol A but starred, so 0 or more A's. So here's my start. I'm going to make this state 23 just so you know you don't have to start at state 1. So my start state has to be an accept state because we accept lambda, right? We're doing A star right now, right? Which is the same as the set A starred. So the first thing here, that's my regular expression, and that's my set, my language. So we have to accept the empty string, lambda, so that does this already. And then as many A's as we see, we accept. So I think we can do this. But if we ever see a B, then we have to go off to our trash state. Right? Does that make sense? Okay, next it says, recognizes language AB star. What's that? AB starred, right? Which is the same as lambda, so 0 ABs, or 1 AB, or 2 ABs, and so on, right? Or, as a regular expression, we might say AB star. So we have to accept lambda. So our start state has to be a double circle, because if we don't see any symbols, we just have to say, yes, I accept. But then we can't accept again until we see both an A and a B. So let's see. If I see an A, I go to state 2. If I see a B, I go to state 3, and state 3 is going to be accept. And then I will accept again if I see another A and then a B. So what if we do this? So if I just see an A, I don't accept it. If I see an AB, I accept. If I see another AB, I accept. Another AB, I accept, and so on. And then we just need to deal with our trash states. So let's make that a loop for A, comma B. And if I'm at state 1 and I see a B, I fail immediately. If I'm at 2 and I see an A, I also fail. And if I'm at 3 and I see a B, I fail. So that recognizes all the strings that have 0 or more ABs in them, and that's it. Okay, let's take a look at this next one. Is A, comma B starred. So that is A plus B star. That accepts everything, right? Including the empty string. So that's going to be nice and easy. So I think this is what we do. We say we accept when we first get in, and we keep accepting no matter what we see. Really easy. Now it says AB star, right? That's a regular expression which represents the set A concatenated with the set B starred. In other words, starts with an A, and then you can have 0 or more B's, right? So we don't accept on state 1 because we have to see an A no matter what. State 2 we do accept. because just an A is okay, or just an A and as many B's as we want. And then we need to make sure it's a DFA, so let's make another state. That will be our trash state. So if we're at state 1 and the first thing we see is a B, we go to the trash. And if we're at state 2, we can only see B's and stay in state 2. Otherwise, if we see an A, we go to state 3. So that's AB star. Let's keep going. The next one we are asked for is to do A, B, quantity starred. But we've already done that, right? This is the same as that. Okay? So these two are the same. This next one, though, right here says A plus B star. A plus B star. So that is we accept an A, and we also accept 0 more B's, but that's it. I don't think we've done that one. So let's see. So here's my start. And if I see an A, I accept. And if I see 0 or more B's, I accept. So I have to accept lambda. So state 1 has to be a double circle. And if I'm at state 1 and I see a B, I go to state 3 and I accept. And if I'm already at state 3 and I see as many B's as I want, I accept. But if I'm at state 3 and I see an A ever, I'm going to reject into this trash state, which in this case is going to be state 4. And if I got to state 2, because I saw that A, and then I see anything else, this says just one A, so I see any A's or B's I need to reject. So I need to go in there. And I think we have an out transition for every letter. Is that true? Looks like it. So that's A plus B star. Now the next one it asks us to do is A plus B, the whole thing starred, right? But that, A plus B, the whole thing starred, that is just the same as something else we did, which is this set here, right? That is exactly the language of A comma B, the whole thing starred. So we've already done that one. And wow, we're actually going to do them all. The last one it's asking us to do, I'm asking us to do, let's be clear here, but I think it's a good example, is A star A. A star A. So A star A means 0 or more A's followed by an A. So really, this is the same thing as the language A plus, right? The set A plus. You remember that in sets we could do this plus symbol, but in languages, but there is no plus in regular expressions, so we have to say 0 or more A's followed by an A. So let's see. You know, if we think about this, if we write it the way it's written, it's kind of, you start with 0 or more A's, but you don't accept yet until you have that final A. Oh, we can't do that, can we? Because now I've got 2 A's coming out of that first state. So that's not going to be any good, right? So we need to think about this a little bit differently. Well, we're using our wits. We'll see what happens. What if we say we start, and you know you're really not going to accept unless you see an A. So we'll accept if we see an A followed by as many A's as we like. That looks pretty good. And the reason this works is this A star A is the same as AA star, right? They're both saying just A's, at least one. Let's make sure we put in all the extra transitions. So 3 will be our trash state. I think that works, right? But this is an interesting one. This is a little bit more interesting than some of the other stuff we've done. We'll talk about this. So the thing that caused us problems on the previous slide was I really wanted to draw this picture that I've got right here, right? Where I have 2 ways to get an A on here, right? I could, two out transitions from state 0 on an A, one which stays here and one which moves. And with a DFA, a deterministic finite automaton, we can't do that. The rules say you have to have exactly one transition out for each symbol. But in this lecture, I told you we're going to learn about non-deterministic finite automata. And the magic of non-deterministic finite automata is, they're almost exactly like DFAs, except these hard rules on whether you that you have to have exactly one out transition for every single letter is gone. You can have 0 out transitions for a given symbol. You can have 1. You can have 23. Doesn't matter. Okay? So an NFA is like a DFA, except you can have 0, 1, or more out transitions for every letter of the alphabet. And if there is no way you can move, there's no out transition for a letter you have in your string, it's not in the language. With an NFA, you're also allowed these things called lambda transitions, which is a transition arrow that's going to have a lambda written on it, above it, below it, whatever. Just like we write A on this transition arrow, we could write lambda on this transition arrow, okay? And we're allowed these lambda transition arrows, which are kind of free jumps. You can take them whenever you want. And since NFAs are more flexible, they have fewer rules in some sense than DFAs, it often is actually easier to make an NFA than it is to make a DFA. Okay, but now you need to know, how do you know if it accepts a string? How do you follow through if there's multiple choices for a path, right? And the answer is that we are going to accept a string if there is any path that processes that whole string and then ends up at an accept state. So for example, if I think about the string that's just a single A, well, a single A I could process in 2 ways on this NFA, right? One way is I could start and I'm at state 0 and I take this loop and I'm still at state 0 and I've used up that A and I say, oh, not accepted. But it accepts it if there's any path that ends in an accept state. So if instead I take my A and I say, you know what I'm going to do? I'm going to decide to take this path today with that single A. That leaves me at state 2, which is in fact an accept state. So the string A is in fact in my language. On the other hand, if we consider the string B, well, I start, I need to process this B, and there is no way for me to do that, and so I lose not in my language. Okay, so we're going to draw an NFA for this language I've got here, AB plus A star A. But let's start by just drawing a DFA for this language. So what does this tell us? It's AB plus A star A. And we looked at this A star A part before and kind of decided that maybe it's easier to represent that part as A star, right? Because it's the same thing. So if I'm drawing a DFA for AB plus A star A, I guess I have my start, and then if I see an A, I end up at state 2. And after that, maybe I see an A and then a B, in which case I accept. That's state 3, right? And maybe I see, so that gives me this A, B part. Or maybe I see this A star A, which is, of course, we said is the same as AA star. An A followed by 0 or more A's. So actually, 2 has to be an accept state 2, right? Because we have to accept a single A. And then we also need to accept more than one A, right? So this A star A lets us have 2 A's or 5 A's or whatever. And what we don't want to do, what you need to be careful about, is we don't want to just put a loop here, right? Because if I put a loop here with that A, then that would allow me to have the string A, B, which is not in my language, right? So it would certainly accept AA, but it would also accept A, B, which is no good. So we got to get rid of that loop. That loop's no good. So I guess in the case of 2 A's, we need to make a new state like that. And what about if we want 3 A's? At this point, I think we can have a loop on that state 4, right? Oh, and state 4, of course, has to be an accept state, right? So now let's just see how we're doing. We're accepting A, then B. We're accepting 0 or more A's followed by an A, which really means 1 or more A's. So there's our 1A gets accepted, 2 A's gets accepted, more than that gets accepted. And we're going to reject everything else, right? So now we got to make our trash state. A, comma, B. And anybody who doesn't meet our criteria goes there. So from state 4, if we have a B, we go there. From state 3, no matter what we have, we go there. And state 1, looks like state 1 on a B has to fail. Let's make a new trash state down here so we don't have to cross lines. And that'll be like that. So this is our DFA for this language. And it was okay. It was a little bit of a pain. Let's talk about an NFA for this language now. And what you'll see here is it's a lot easier to make an NFA for this language than a DFA. So let me just show you what's going on here. So here's a few possible strings we could look at. And hopefully if you look at these strings, you'll agree with me that AAA is in this language, and so is AB, but ABBA is not in the language. So let me show you how both this first and second string are in the language for both of these NFAs, and how the middle string is not. So if we consider this AAA string for a minute, remember we know it's in the language if there's at least one path through the NFA that leads to an accept state and processes all the letters. So right now I'm just going to show you that one path. I won't exactly show you how I figured out that was the one path, but I'll show you the path. So with this first string, what I'm going to actually do, I have to start at state 0. And then before I do anything, I'm going to take this lambda jump, because you can take a lambda jump whenever you want. I'm going to decide before I even start processing symbols in the string, I'm going to take a lambda jump. Then I'm going to process the first A by taking that loop. I'm going to process the second A by taking the same loop again. And for the third A, I'm going to take that transition. I'm done processing the whole string, and as you see, I'm at a double circle, so I accept. So what I've shown you so far is that this string, AAA, is accepted by the top DFA or NFA here. Okay, let me show you how it's also accepted by the bottom one. So in the bottom one, what I'm going to do is I'll start processing this first A. I'll take that first transition to state 3. I'll process the second A, take that loop, and the third A, take that loop. I end up at state 3, which has a double circle on it, so I accept. So both of these DFAs definitely accept this string AAA. Now, I haven't told you how I realized that that was the path I should take, right? There's other paths through these, but you hopefully agree with me that it accepts it. We'll get to the how do you pick the path in a minute. Let's skip that middle one for a minute and just show, just show how AB is accepted by both of these. And that should be pretty easy, right? If I started state 0 and I take the A for the 1 and then the B, I end up at state 2 here, which is an accept state. And similarly on this machine, if I started state 0, I take A, 1, B, 2, and I'm in accept state. So now we have to do something a little bit harder. I just want to show you that ABBA is not in my language. I mean, you know ABBA isn't in my language because it's not in this regular expression, right? It's not in the language represented by that regular expression. But I want to try and show you that there's no way you can get through these NFAs and recognize that string and end up at a double circle. So there's a couple of options. And let's just try them all. If we're on the top NFA, one option is we start, and before we even do anything, we take that free lambda jump. And then we see A, B, B, A, so we could try, like, maybe do that A first. Oh, but if we do that A first, there's no B, so, right, there's nowhere to go, so we lose, it's not in there. So maybe what we did is take the lambda and then that A, but again, there's no B, so we can't do it. So maybe those paths were the wrong one. Maybe what we're supposed to do is take this A and then this B. But again, we get to state 2, we don't see, so we process the A, we process the B, but we don't see that next B. And if there's no transition to let us get through all of these letters, we fail. So I've shown you that ABBA is not accepted by this first NFA. No matter how you try, it's not in there. As far as the second NFA is concerned, it's even easier to show, right? We try to process this first A, and, well, we could take that one. But once we've done that, we process the B, and there's nowhere to go, so we fail if we take that A as our first one. If we take that A as our first one, and then the B, that's fine, but again, we're stuck. We can't do anything with this next B. So this bottom NFA does not accept that string. So let's talk about this problem for a minute. It says, how would you make an NFA for the language A plus B quantity starred A, right? So that's as many A's or B's as you want, and then an A, right? And for the NFA, this is really easy, right? For the NFA, we start at state 1, and I guess at state 1 we see bunch of A's and B's, and then, but at some point we need to see an A that takes us out to state 2, and we accept, and we're done. That's our NFA. We don't need a trash state anymore because we don't need an out transition for each step. We're just done. The DFA for this string is a lot harder. Let me take this guy and move it up there. Oh, we got that line too. Oh well. If you think about making a DFA for this, one of our problems is, of course, that this thing we've got up here has, from state 1, 2 transitions that leave with an A, right? So we can't use that. We need to start thinking a little bit differently about this. We kind of have to say what's in here. It's as many A's or B's as we want with at least one A at the end, right? So I guess what we have to do is we have to say, well, we start, and if we see a B, well, let's think about this. We can see as many B's as we want as the start, right? So I guess we could have a loop for a B there. If we see an A, we don't really know whether the A that we're seeing is the last one that we're going to see, or it's just the first A in a bunch of A's and B's. But regardless, if we see an A, state 2 has to be an accept state, right? Because we accept the string that's just the letter A. And once we get to state 2, if we see another A, we're okay. We can kind of stay here. But if we see a B, is this it? Do we have to go back to state 1? Because we can't stay at state 2 with B because we have to end with an A, right? So this doesn't look bad. Let's see. We could always analyze this almost by saying, look, if you look at state 1 is kind of represents, I haven't seen anything yet, or the last thing I saw was a B. Whereas state 2 represents, how do you get to state 2? Well, you get to state 2 if the last thing you saw was an A, right? So state 2 is always going to be an except state. But if you see a B, you go back to 1 and you hang out in 1 with your B's until you see an A, and then you hang out in 2 with your A's. So this looks pretty good to me, except it's still not a DFA, of course, I think, because it doesn't have, oh, it does actually have an out transition for everybody. So we're good. So there's our DFA. But, you know, if you look at this and compare this with our NFA up here, it was a lot harder to think about that. Okay. Here are a bunch of very important facts about regular languages, about NFAs and whatnot that you need to memorize these. These are important. You need to understand them and remember them. Okay? So let's just go through them. The first thing is regular languages are sets of strings. Well, we know that, right? Because you know that every language is a set of strings, so regular language are sets of strings, not a surprise. Every regular language can be represented by a regular expression. Well, that also shouldn't be a surprise. That's something we did a while ago. And same with the other way around. Every regular expression represents a regular language. I told you earlier, every regular language can have a DFA built to recognize it. I'll tell you now that every regular language can have an NFA built to recognize it. But you actually already know this, right? Because anything that you have that is a DFA is automatically an NFA, right? All DFAs are NFAs. If I show you something and say this is a DFA, you can instantly tell me, oh, it must be an NFA as well, right? Doesn't work the other way. If I show you something that's an NFA, it may not be a DFA because it may have 2 out transitions for the letter B, or it may not have an out transition for some letter. But if it's already a DFA, the DFA rules are much stricter. If it satisfies the DFA rules, it satisfies the NFA rules. And if you've got a language recognized by a DFA, it's regular. If a language is recognized by an NFA, it's regular. Whoops, and I got ahead of myself on the last slide, right? Are all DFAs NFAs? Absolutely. Any DFA that you have, you know, you've got your A, and this one has a B, and if we're making it into a DFA, then we got to make sure we've got a B transition, an A transition. I don't know, we could do something like that. I guess we should have somebody except, or it's pretty boring DFA, but there's a DFA, right? And I can just say, poof, actually you're an NFA, and magic it's an NFA, right? On the other hand, if I have an NFA, like this one, this is the NFA that accepts the language A, right? Just the symbol A, which is represented by the regular expression A, right? But there's no out transition for B from state 1. Oops, I didn't write start on this one. Tisk, tisk. And I didn't write start up here. But down here, no out transition. Well, who knows? Maybe it's just a lang over the alphabet A, but there's no out transition for A on state 2. So not a DFA, but it is an NFA. So problem from the book. Use your wits to construct an NFA for the following expression. I think we did this, right? But let's do it very quickly. So we can have as many A's or B's as we want to start out with. But we don't accept yet. We don't accept until we end with an A, right? And that's an NFA for this. Making this into a DFA is harder, and you can see it's going to be harder because there's an out transition for A there and an out transition for A there. It's possible, if you have an NFA, it is possible to make a DFA that recognizes the same language. But just because it's possible doesn't mean it's necessarily easy. So here's a couple of questions. The first question is, I tell you this is an NFA, but is it a DFA? And the answer is no. You can tell this for a bunch of reasons, right? Most obvious to me, the thing that jumps out at me is it's got lambda transitions, and we never have lambda transitions in our DFAs. It also has 2 out transitions for symbol A out of state 0. And it doesn't have any B's out of state 0, so it's not a DFA for a pile of reasons. Now, figuring out the language it accepts is a little bit trickier. Let's see. What have we got here? If we look at the path that kind of allows us to go through the top of this thing, we've got as many A's as we want, and then a free jump, as many B's as we want, and then at least one B and one A, and that gets us to an accept state. So let me just squidge this a little bit so we have a little bit of room. So at least part of the regular expression for this is going to be A star followed by a B star followed by a B and an A. That's definitely in there. We can also get to state 3 by taking this jump. So we kind of skip the first part, so we just have one A followed by an A. So we have A's in our language. But then, if you look, we've got this lambda back here. So what is this telling us? This is telling us that when we get to the end, oh, look at that. That kind of makes an A star, right? So this is essentially saying to get to state 2, you need to either have this stuff, right? So to get as far as state 2, you either need a bunch of A's, 0 more A's, free jump, 0 more B's, followed by a B. Or another shortcut to state 2 is you just have a single A, right? And once you are at state 2, you can add on as many more A's as you like, right? Because once you're at state 2, it can have A, A, A. So in fact, probably a better way to write this, let's kind of cross that out, would be you can start with A star, B star, B to get to state 2, and then have as many A's as you want. Or you can start with A to get to state 2, and then have as many A's as you want. So I would say that's my language. Another, is this a DFA? And if you look, it should become obvious very quickly. There's no out transition for B on state 0, so since there are out transitions for B in other places, we know B's in the alphabet, not a DFA. And what language does it accept? Let's shrink it a little bit so we have a little bit more room. Well, this is interesting. Okay, so it looks to me like we have this backwards guy again, right? And so there's this like transition to state 3, which is where we finally win, but we have an A, as many B's as we want, an A, as many A's as we want. And then optionally, if we have a B, we can kind of repeat that piece. Let's build this up slowly like we did with the other one. So we could start with an A, right? So this A, oh, in fact, you know what? It always has to start with an A, right? And it always has to end with a B. So it's A followed by a bunch of stuff and then a B. And what is the stuff in the middle? The stuff in the middle is we can have, well, we have to have this piece here at least once, right? So the piece in the middle, maybe I'll do the piece in the middle in green. That piece I've just circled in green is going to be B star, A star. And after we've done a B star, A star, we could do it again as long as we start with a B. Let's kind of circle that in red. So if we start at 2 and we go back and do it again, then we end up with a B followed by a B star, A star. So what have we got here? I guess we start, where can I write this so I have a little bit more space? Let's see, can I squidge this? Oh, everybody squidges, that's good. Okay, so let's write our final answer. None of these are quite there yet. We'll write our final answer in blue. So, let me stretch this just a little so you see it. So, like I said, we have to start with an A no matter what. And then in the middle, we have to have a B star, A star. And of course, by have to have the B star part, it could be no B's at all, right? We could skip that, but B star includes lambda, so we've got an A, 0 more B's, an A, 0 more A's, and now we're at state 2. And then before we go to state 3, we could have a bunch more of these things repeated if we want, right, to get us back to state 2. So I'm going to say after that we can have a B followed by B star, A star. And the very last thing we have to have, I don't know if you can see it because I've kind of written over it, but is the letter B. So there's my final answer. You have to start with an A, right? Start with an A. Then, in order to get to state 2 and be ready to leave state 2, you have to have 0 more B's followed by an A and 0 more A's. So that's this piece. And then you can optionally do this as many times as you want, right? Oh dear. Did I really not put a star out there? So optionally, you can 0 or more times, you can do this B star, A star, right? That whole piece can happen 0 more times, and then you have to end with a B. Okay, a bunch more practice problems. My suggestion is you try these on your own before you watch me doing them in the video. I'm going to go through them relatively quickly. Also remember, of course, that there's lots of ways to solve these, and just because you don't get the same answer as me doesn't necessarily mean that you're wrong. So let's just go through these, a bunch of these. All right, so the first one we're going to do is A star, B star. So that's as many A's as we want, followed by as many B's as we want, but they have to be in that order, right? We can't mix the orders of the A's and B's. And this is where lambda transitions come in really handy, because I could say, all right, well, let me have 0 more A's, and then I'll do a free jump, and we'll make state 2 an except state, and I can have 0 or more B's. So that's a nice, quick and easy NFA for A star, B star. And let's see, let's put that up there. If I want A star plus B star, that's different. That's all A's or all B's, right? So we can have, let's see, we'll start, and it's 0 or more A's or 0 or more B's. I'm going to use that lambda transition again. Lambda, state 2, 0 more A's, or lambda, state 3, 0 more B's. All right, let's put that one maybe there. I'm not going to have room for all of them, but we'll see. Oh, and now I have A star, B star plus B star, A star. So either starts with A's and then ends with all B's, or starts with B's and ends with all A's. So actually that's going to be somewhat similar to this guy. What we're going to do, let's do it in a different color. What we're going to do is, and again, there's lots of ways to do this, but I'm just showing you kind of what seems most natural to me. I've got two choices Whenever I have two choices like this, it makes it easier for me if I just do two lambda transitions. So the first choice, my A's followed by my B's, is going to be exactly what I have above. There's my A's. I've got a lambda transition to state 3, which will accept with my B's. Or maybe I want to start with my B's and then lambda transition over to here and have a loop with my A's. Okay. The next one is A plus B quantity starred. I'll do that in red. So we have A plus B and the whole thing starred. Well, that's, if we're just over the alphabet AB, it accepts anything, right? So we've got our start, and we accept anything. That was easy, right? All right. And the last one is A plus B starred followed by an A. And again, I think we've done this before, but maybe it's just very similar to what we did before. We're going to have our start, as many A's or B's as we want, and in the end, we have an A, and we go to state 2 where we accept. Now, notice that, again, you need to make a decision. If you're looking at a particular string, like you're looking at the string A, B, B, A, right? When you look at that string, in order for it to be accepted by this NFA, there has to be at least one path through here that ends in an accept state. So I'm going to say, all right, well, A, B, B, A, that works, uses all the letters, ends at the accept state. We, again, have not talked about how do you know which path to take, right? We're not there yet. Okay, I think it's time to start talking about how you decide when you look at an NFA whether a string is accepted by that NFA or not. And so far I've just said, by definition, it's accepted if there's any path through the NFA that uses up all the symbols in the string and also ends at an accept state. But there's a little bit more to it than that. I mean, that may have left you feeling a little bit uncomfortable. And I'm not promising you that you'll feel hugely more comfortable after this slide, but I want to talk to you about the two different ways that computer scientists think about how to think about processing through an NFA. So here's an NFA we've seen before. It's an NFA that accepts the language AB plus A star A. We've seen other NFAs that also accept this language, but this one is a good example to work with. Remember that this language is a set of strings, because all languages are sets of strings, and the strings that are in this language, well, there's the string AB is just a string in the language. And other than that, it is all strings that are made up just of A's that have at least one A, right? So we could kind of write this out as a set, as the set containing AB unioned with the set containing A, dot, dot, dot. Right? Okay. So I want to take one of the strings in this set. Let's take a look at the string A. And first, let me just show you that it is it's accepted by this DFA, right? I hope you agree with me, but let's just take a look. So if we follow this DFA as follows, we start at the start, and then before we do anything, I just decide to take a free jump. I take that lambda, and then I'll process the first A by going around, I'll process the second A by going around, I'll process the third A by going around, I'll process the last A by going along that transition there. I end up at state 2. State 2 has a double circle, so it's an accept state. And since I have used up all the letters in my string and I end up at an accept state, I say, yep, my string is in the language. So that's good, but how did we know to take that? In other words, how did I know I should have taken this path to start and not ignored the lambda jump and taken that one because I did have an A, right? I could have gone from 0 to 1. So, you know, that's a little bit tricky. How do we know that? So what I'm going to do, let me clean up the screen. And we'll just write the string that we're thinking about up here at the top. And let's talk about the two ways that computer scientists tend to think about how an NFA processes. Okay? So the first way that some computer scientists like to think about NFAs is kind of the magic approach, right? So here's my stars. Now I get to show off the little stars that I have in this nice software, right? And the magic way of thinking about how an NFA processes a string is you just say, okay, the NFA always guesses right. So when we are processing this string with 4 A's, the NFA, of course, that when we're processing the string, we start at state 0 because that's the start state. And then magic, right, we just kind of, can I wiggle the stars? No, I'm wiggling the page. That's not very good. I'm still not wiggling the stars. That sucks. Oh, well, okay, so magic, we just say, okay, I'm at state 0. I think I'll take this transition from state 0 to state 3, which is totally legal because it's a lambda transition, so I can take it. And then I need to decide, what do I do next? And I say, well, magic. Are you impressed? That's the magic of video. I paused and got the stars to wiggle. Okay, so I decide magic. I am currently at state 3. And I have a letter A to process. There's no lambda transitions. Magic, I pick this one, right? That A's done. So next step, no lambda transitions. I want to process the next A. And so what do? Well, I say magic. Forget it, I'm not moving the stars anymore. It's too hard. See if I try to move them. Yeah, I draw. So regardless, magic, I'm processing the second A. I'm going to take that loop again. All right, that A is processed. I'm processing this A. Magic, I always guess right. I guess I'm going to take that one. Cross that guy out. Process this one. Magic, I think I'm going to take this transition this time because that's the one I think I should take. I take it, and I end up at state 2, and look at that, I've processed the whole screen, sorry, I've processed the whole string, and I end up at an accept state. And this is really, I mean, computer scientists talk about processing strings by saying that, yeah, the NFA just picks the right path. Now, for some people, that is perfectly acceptable. If you like to think of it as pick the first path, totally fine. For me, that makes me a little bit uncomfortable because I'm trying to think, how the heck does it know what the next path is? So I'm going to show you another way of thinking about this that might make you feel better. So let me clean up the screen again. And this time, instead of magic, we're going to kind of keep track of all the places we could be at any given time, okay? And so, you know, when we start, of course, we think of ourselves as starting at state 0 because that's the start state. But before we do anything, before we make a move ever, we're going to take into account any lambda transitions that we have. So we're going to think of this as kind of a two-stage process. We will take lambda transitions, then we'll process a letter without thinking about lambda. Then we'll take lambdas, then we'll process a letter without taking lambdas. Okay? So if I look at this system and I say, is there any lambda transition I could take from 0 that would start me anywhere else? I say, oh yeah, look at that. I could move from 0 to 3. So what I'm going to say is during my setup kind of follow lambda transitions period, I could start at state 1, or say 0, or state 3. So I could kind of keep track, and I could write, I'm at one of those two states, right? It's a set of states, 2 states. And then I say, all right, now let's process this first letter. And where can I get to if I process an A? And if I process the A, and I'm starting at state 0, right, which is one of the possibilities, and I'm ignoring lambdas now, then it looks like my only choice is to go from state 0 to state 1, right? If I'm starting at state 0 and I'm processing an A, then I can go from state 0 to state 1, right? So now I know that one of the places I could potentially be at is state 1. And let's take this arrow and rotate it a bit so it's out of the way. All right, so one of the possible places that I can be right now after processing that first A is at state 1. Before processing that first A, I could also have been started at state 3, right? And if I started at state 3, it looks like there's actually 2 places I could end up, right? Because I could do that loop and stay at 3, or I could follow this transition and end up at 2. So now if we look at where I could be, I could maybe be at state 3 or state 2. So that's after processing that first A. Okay. And now what we do is we say, okay, in between processing we take any possible lambda transitions. Well, there aren't any, so let's go on and let's process the next A. And when I process that next A, I have to go through every single one of these states that I could be at and see what happens. So if I'm at state 1, and I see an A, there's nowhere to go, right? So that state kind of, or this arrow here, goes away. We can't be at state 1 anymore, and we can't move from state 1. So I'm going to say that this arrow, gone. All right. If we start at state 3 and we process this A, there are 2 possibilities, right? We could do that loop, or we could do that. So 3 and 2 are still possibilities. If we start at state 2, oh, look at that. We kind of fall off again, right? There's nowhere from state 2. So we can get to state 2 from state 3, but this arrow that started at state 2 can't get anywhere. So really kind of what we need to think about doing is when we're considering what can I do from state 2, well, the answer to what can I do from state 2 is nothing, because there's nowhere this guy can go. So we delete that guy. But then I say, well, where can I go from state 3? And I say, well, I could stay at state 3, or I could go to state 2. And so I pop an arrow back in there. So after I process that second A, I could be at state 3 or state 2. And now we process the next A. And you can see that if we process the next A, we're starting out at state 3 or state 2. So if we're at 2, well, we can't do anything, so that arrow goes away. If we say, oh no, maybe I was at state 3, we could take that loop, or we could take that arrow, and so presto changeo, we have a possibility of being at step 3 and step 2. I shouldn't say presto changeo, it's not magic anymore, right? We figured out all the possible places we could be, and after processing that third A, all the possible places we could be are state 3 and state 2. All right, and now we process that last A, and I'm sure you'll see again that after we process that last A, we end up saying we could be at state 3 or state 2. Or state 2, right? And then what we do is we look, because now I've processed all the letters in the string. So at this point, I say, let me look at all the possible states I could be at after I process all the letters in the string. Are any of those states final states? Well, 3 is not a final state, but look, 2 is a final state. So that means there is, in fact, a path through this NFA that takes me to a final state. So again, there's 2 ways to think about this. As far as the NFA definition is concerned, it accepts a string if there is some path, if there exists a path from the start through the NFA that eventually takes you to an accept state having processed all the letters in the string. Okay? And some people like to think magic, the NFA just knows which path to take every time. Some people like to say, let me think about all the possible places I could be at any time step and see where I get. And when I get to the end, let me see if any of the possible places I could end up with is an accept state. So you get to decide. Now, of course, so far our explanation of what an NFA is has been somewhat informal. When we did Dfas, we started out with an informal definition, and then we came to a more formal description of our DFA as a 5-tuple. And so let me start by saying, could we use this same representation for an NFA? And, you know, obviously this transition table won't work for us as is because we don't have lambda transitions on it, right? So we could imagine adding a space for lambda. And the question is, does that work, right? If we just add the lambda transitions, does that give us what we need to represent an NFA? And the answer is we are close, but we're not quite there. Because if we have an NFA, we could have, say, 2 ways to leave state 0 with the symbol A. And we don't have a way to represent that in this table. Okay? So we need to change our formal description of a DFA in order to be able to represent a formal, in order to be able to represent an NFA formally. So as you might have guessed, it's going to be very, very close, but it's not exactly the same. So the first difference that you'll find, and all the differences are in the transition table, right? If you look at this, we still have the states followed by the alphabet, transition function, start, and final. The states, still a set. The alphabet, still a set. And remember, our alphabet doesn't contain lambda. Remember from the very beginning, lambda has never been in our alphabet. Lambda is a special symbol that represents the empty string. We'll skip the transition function for a minute. Start state is still just a single state, and final states can be a set, so we represent it like that. And so as you've probably guessed, if you'd look at this transition table at all, the 2 big differences that we have now are, first off, we've added a column for lambda, like we talked about before. And secondly, we've switched things here. Now, we don't just have a singleton in each space in this table, right? Instead, we have a set, okay? So every single thing we fill in here has to be a set, because if you start at 0 and you take an A, we could have 0 places it goes to, 1 place it goes to, 2 places it goes to, as many as there are other states. So if we look here, and I say I start at 0. On an A, I could end up at 0 or I could end up at 1. So over here on my table, I say I've got the set 0, 1. If I start at 1 and I have an A, well, there are no out transitions from state 1 on an A. So what do? We write the empty set, because that is a set with nothing in it. Got it? Okay. So let's look at here, 2 on A, right? If we start at 2 and we have the letter A, the only place we can go to is state 3. So we put that, even though it's just a singleton, you know, if you have a function, think about a method in Java, right? Your method has to return a single type. In the case of this transition table, our method is returning a set. Okay? And I'm going to be very nitpicky on this when I grade stuff, especially on the exam. So make sure you've got this straight. When we were talking about a DFA, we had just one possibility here, and there was no, right? There was no column for lambda because no lambdas in DFAs. But now that we're talking about NFAs, we have to add this column for lambda, and every single element of this table has to be a set. So just take a look at this slide for a minute. This diagram that I have up here on the top is a picture of a DFA, right? And you can look and you can check and you can say, yeah, it's definitely a DFA because every state has an out transition for every letter of the alphabet, assuming, of course, our alphabet is just limited to A and B, but we'll assume that. But of course, you could say, oh, you know what? This is also an NFA, right? There's no rule that says you have to have lambda transitions for NFAs. There's no rule that says you have to have more than one output for some letter for an NFA, right? And what I want you to look at is just these two formal representations of our DFA and our NFA. So if I say, this is a DFA, then I have to represent it the way I show you here in green, right? And if you look at the green stuff here, everything is the same between the NFA and the DFA in terms of this 5-tuple, except for that transition table, right? And if I say, oh, it's a DFA, then the transition table only has columns for A and B, right? And every element is just one singleton. On the other hand, if I say, oh, no, I meant this to be an NFA, and I talk about my transition table for the NFA, then I make sure that I add a column for lambda, and every single thing that goes in here is a set. So I just fill in lambda with the empty set because there are no lambda transitions, right? Really, really important that you understand the difference between these two. All right, so let's just do an example. We'll do this problem from the book. We'll write down the transition function for this NFA. Let's move it out of the way a little bit. So let's see. And it just says the transition function doesn't even want us to do the 5-tuple. So what have we got? In terms of states, we've got a state 0, 1, 2, and 3. And our alphabet seems to be A and B, and then we also have lambda. Okay? So if we are at state 0 and we see an A, it looks like I can go to state 0 or go to state 2. If I'm at state 0 and I see a B, there's nowhere, no transitions from there, so empty set. And state 0 on a lambda can take me to state 1, so I put that in curly braces, right? If I'm at state 1, I think there's no way on A. B can go to states 1 or 2, and there are no lambda transitions from state 1, so that gets the empty set. If I'm at state 2, well, 2 on A can get me to state 3, and there's no other outputs from state 2, so those are both empty set. And finally, 3 only has one output, which is a lambda transition from state 3 to state 2. And otherwise, we've got the empty set. Now, here's a perfectly reasonable NFA, and we're asked to give the 5-tuple for this NFA. Notice that state 2 is just, out there. It's not going to do anything, but it exists, so we need to include it. And furthermore, it looks like we've just got the alphabet AC. And since nobody told us any different, we will just assume that's our alphabet. So let's shrink this down a little bit so we have some room. And our 5-tuple, as you remember, the first thing we do in our 5-tuple is we say, what are the states? So It's a set of states, so we have states 0, 1, and 2. Next thing we do is we say the alphabet, and our alphabet looks like it's A and C. I will just write T for the transition table. The start state is 0, and there is only one except state, which is state 1. All right? And now let's just take that and move it out of the way a little bit so we have a little bit more room. Oop, I'm going to squish it a little bit more because it's really, really important to me that you see I have a closed parentheses on there, right? It's a 5 tuple, so it starts and ends with parentheses, but there are some sets inside of it. Okay, so I don't know if that's actually big enough for you to see this picture. What if I do like that? All right, so now let's draw the transition table. So let's see. My states are state 0, 1, and 2. My alphabet is A and C, and I also have to add in a column for lambda. 0 on A goes to state 1 only, and there are no outputs from 0 on C or lambda. In fact, if I look, I don't see any lambda transitions here, so I'm just going to fill that in right now. If I'm in state 1 on A and C, I stay at 1. And if I'm on state 2, A and C, I stay at 2. All right, so T equals. Good. Okay, some more NFA practice. Use your wits to construct an NFA for the following regular expression. A plus B star A. All right, so let's kind of move that up there. And just so you understand, that's just part B. So we're trying to figure out A plus B quantity starred A. And I like to do, you know, I think when you do an NFA, you just kind of go for it and feel free to use lambda transitions if you need them. I don't know if we will, but let's see. So we're going to have our start at state 1. And let's see. You can have as many A's or B's as you like to start before you do anything. So I think we'll just do a loop here. And then we need to absolutely end with an A. And then we accept. That was easy. Okay, here's a couple more problems. Oops, sorry. Again, we're going to use our wits to construct NFAs for these two expressions. So let's start with A star B star. So if I'm trying to do an NFA for A star B star, I will start. And this is, of course, as many A's as I want, followed by as many B's as I want, but they do have to be in that order. So let's start by having state 1 have as many A's as it wants. And here's what I meant by liberal use of lambda transition. The lambda transition, I cannot, what I absolutely cannot do is I can't put in here A comma B, right? I can't do that because then the A's and B's could be in the wrong order, so I can't do that. So what I need to do is say, well, do all the A's you want to start, take your free jump, and then do all the B's you want. And in fact, you don't need any B's, so we can make that our double circle. Okay. In contrast, the other one that we need to do, let's do that in blue, is A star plus B star, right? So this is strings that are just A's or strings that are just B's. And again, lambda transitions are going to help us lots here. So we're going to start at state 1. And I'm going to say, and a lot of the time, if you have a plus, right, that's our union, just kind of think, oh, would lambda transition help me? So I'm going to immediately lambda into 2 possible cases, all right? And over here on the left is the case where I have 0 or more A's, and I do accept with 0 A's. So state 2 is going to be an accept state, and it's just going to have a loop with A's. And down here on the bottom, state 3 is going to be kind of the same, right? An accept state with all B's. All right? So there you go. time to go off and do your own NFA practice problems now.